Alright, so today, I know that I promised to move over to other topics, but I thought that it would be helpful to do instead some examples of Fourier series. We're going to do a couple of sine Fourier series, one cosine Fourier series, and a full range expansion. Now, if I ever tell you compute the Fourier series for a function, it will be just a periodic function, right? And then you know how to do it. You take one period and it's a full range. It's the same as the full range expansion. But in general, if it's a function that is not periodic, I will ask you to compute either the full range expansion, which means take the periodic extension and compute the Fourier series of that is periodic, or the sine expansion, then take the odd extension and compute the Fourier series of that is periodic, or if I ask you for the cosine Fourier series, it would be the even extension and compute the Fourier series of that one, all right? Because remember, Fourier series only exists for periodic functions, but then we can reproduce any function in an interval by getting that interval and making it periodic. In the different ways we can make it periodic. So, I wrote an example to begin with. I asked you to find the Fourier sine series here for the function f of x equals x, one function that we dealt with already, but it's going to be in the interval minus L to L. X is between minus L to L. So very similar to things that we've already done, but it's a good warm-up. So let's do this example. As always, the first thing that we need to do is to draw the problem. So let's draw the function in the region minus L to L. So this is a simple one because this is a straight line, so 45 degrees, like that. Slope 1. So you get this is the function from minus L to L. Of course, this function would actually continue everywhere, but we don't want that. We want to do is the sine series. So what we want to do is the odd extension. So we're going to compute the odd extension that we call h of t, that will call h of x, sorry, because the variable is x. It will coincide with f of x between minus L to L, but then it will be the odd extension of f of x. Alright, so let's remember how we do the odd extension. The odd extension, we do it by taking the axis of symmetry, take this one, right, for example. And then we want that on both sides of the axis, when I move the same distance, it would be the same value but with negative sign. So this thing would be this one. Same height here. This should be 3L. And here, same thing. Invert the sign. So we start here. Right? So you can tell that this is just writing this and prolong it an infinite number of times to the right, etc. Right? If I were to draw even more, this thing will start here and go up. All right. Wonderful. Now, we know the Fourier series in general has an A0, it has an AN, and it has a Bn. Now, for the Fourier sine series, we know it's an odd function because it's the odd extension, so there will be no cosine series. All right? Perhaps for this case, I'm gonna again write all the terms and we're gonna see that there's no AN or A0. But in general, it would be enough just to start computing the Bn, okay? First of all, what is the period of this function? What is the period of the odd extension? Well, the period is capital T equals 2L. You see, it repeats every 2L. So the period is 2L.
All right, let me stop this for a second to make a clarification. I'm going to operate in this exercise with a period t equals 2L. Obviously, the function is periodic with that period, and the series that will result from that will be a sine Fourier series. However, technically speaking, the odd extension should have a periodicity that is twice the interval of the original that we took from the original function. That would be a period of 4L, because the original interval is from minus L to L. So technically speaking, the sine Fourier series coming from the odd extension should have a period of t equals 4L. And to be completely correct, we should have operated with a t equals 4L, and that's what I should have done. Now, of course, in this case, what's happening is that the graph of the odd extension coincides exactly with the full range extension. You can tell if you just take the function in the interval minus L to L and copy and paste it to the left and the right infinitely many times, you get exactly the same graph as you got from the odd extension. However, if we were to compute as technically we should with the 4L period, we would get a slightly different Fourier series, which is still a sine Fourier series, so both are sine Fourier series. So in this case, it is okay to operate with just half the period of what the extension should have, because it's periodic still. The two series that you obtain are easily relatable through trigonometric identities. However, in this exercise, I'm going to be operating with 2L. I just wanted you to remember that technically speaking, the sine Fourier series coming from the odd extension should have been computed on an interval of 4L. In this case, and oftentimes when we compute the sine Fourier series, if the function happens to be like this one that is periodic in half of the period, we just go with half of the period and say 2L. But just remember the technical point that, as we saw in the definition of the odd extension, the period should be twice the length of the interval, and in this case would be 4L. All right, back to the video.
Okay, and then omega, the frequency, which is 2 pi over the period, is 2 pi over 2L, so pi over L. All right, wonderful. So now we know that the Fourier series would be h of x would be, let me just write h0 divided by 2. We know this is going to be 0, but let's just write for completeness and we'll check this one more time, but we're not going to check anymore because for parity reasons that's always the case for the other extension. Sum n equals 1 to infinity an cosine of n omega, I'll just write it with the omega here without substituting, n omega x plus sum n equals 1 to infinity bn sine n omega x. All right. Now, of course, the coefficients, I'll write them here. an is equal to 2 over the period integral from t0 plus capital t0 to t0 plus capital T of the function, which in this case would be h of x. And then if it's an, it would be the cosine of n omega x dx. And the n is 2 over the period integral t0 to t0 plus t hx sine n omega x dx. All right, so let's quickly deal with the a0 and the an. So a0 is of course 2 over the period, and the period is pi over L. So it's 2, so over the period, right? So 2 over 2L, right? And then this is the integral. So let's take a period. So we need to pick t0. In this case, picking t0 minus L makes the easiest because I don't jump. I don't want to get the discontinuities to make it easier. So the function is always, this function h of x is not t everywhere. It's only t from minus L to L. From here it's not t. It's t but translated, right, to the right. So subtracting some quantity. Anyway, so we're going to start from minus L to L. All right, and then we have the function h of x. I'll write h of x, which is what it is. And then I have the cosine, well, I'm doing a0, right? So that's 1 dx. That's very easy. This is an odd function, because the odd extension, see how odd it is though. It's the area here is the same as the area here. The integral of this is directly 0, because this is an odd function. So an, in this case, is 2 over 2L, integral from minus L to L, h of x, cosine of n, omega is pi over L, x. This is an n. All right, dx. All right, so in this integration region, it's clear that this function is odd, the cosine is even, so the product of the two is odd, and then the integral in a symmetric interval is 0. So there's no a0 or an. In fact, we will no longer, when I say the sine series, I will no longer write the cosine terms because we know they're going to be 0 because hx is odd and therefore is orthogonal in this inner product with all the cosines. All right? All right. So we know there's only sine terms. Let's compute the bn's. Now bn is 2 over 2L integral from minus L to L h of x sine n pi over Lx dx. Now, from minus L to L, h of x is just t. So nice enough. And in fact, it's not even necessary to do it like this, because I could do this. Remember, this is an odd function, odd. This is an odd function. So the product of the two, it's even, which means that in a symmetric interval, in an even, so the 2 and the 2 cancel, let's write it like that, so I have 1 over L, and then I can write this as twice the integral from 0 to L of h of x, I'm going to substitute by t, all right, t, right, there we go, sine of n pi over L x dx. All right, so this is the expression of the BDMs, and this integral can be done by parts, with integration by parts. Now, I'm going to do the steps of the integration by parts. I mean, some of the steps, I generally won't do them, but I'm going to write, you please do the integration by parts here. It's t times the sine, so not very difficult. So the prefactor that one gets, the 2 over L, of course, that is there. And then I get a prefactor that is L divided by n squared pi squared, all right, and that multiplies L sine of m pi xl, all right, minus n pi cosine of m pi xl, evaluated from 0 to L. Okay? If I evaluate at the limits, that's easy. You know, and we evaluate at the limits, what we get. The cosine of 0 is 1, the sine of 0 is 0, then when less than L, this becomes sine of m pi. Well, I'll write it. This is equal to, right, I'm going to get 2, I'm going to simplify a bit, 2 m pi n squared pi squared. And then this is, let's see, L sine of m pi x divided by L. Oh, sorry, no. Sine of m pi. Okay. Minus L n m pi L cosine of n x m pi. Sorry. There we go. That's what you get when you simplify it. All right, wonderful. Now it's clear that the L's cancel, right? All right, so now, again, technically, those are the coefficients, but what we're going to do is simplify this, because we know that, let me write it here. We know, and write it here, that the sine of pi n, or n pi, is 0 for integers, and the cosine of n pi, we've done it already, is minus 1 to the n. Remember, cosine of 0, 1. Cosine of pi, minus 1. Cosine of 2 pi, 1. Cosine of 3 pi, minus 1. Alright, so if we do that substitution, what we get is that this is equal to 2 n pi n squared pi squared, and then L minus 1, sorry, m pi minus m pi, this is 0, that's the point, 0, and this thing is minus 1 to the n, okay, n pi minus 1 to the n, yeah, but with an L, I'm missing the L, okay, n pi L, yeah, this L is this L. Wonderful, we can simplify this and write, simply put the minus sign in here, and we're gonna get the following. So this is 2L, n pi cancels one of the n pi's in the denominator, so n pi minus 1 to the n plus 1. So what I did is I put this minus sign as an extra minus 1 in here. All right, so that's it, that's the B. So that means that we can now write the Fourier series, because this is, remember, this is Bn. So the Fourier series h of x, the sine Fourier expansion, the sine Fourier series is sum n equals 1 to infinity of, and I substitute Bn, which is 2L divided by n pi, and then minus 1 to the n plus 1, and then I get the sine of n pi divided by L times x. All right, so that's it. And I'm gonna simplify a bit, just for fun, taking the constant values out of the sum. So this is 2L divided by pi, sum n equals 1 to infinity, minus 1 to the n plus 1 divided by n, sine of n pi over L times x. And this thing is h of x, which is the solution to the problem we are asked. So you can tell, not extremely difficult. All right, let's do another example. Okay, so here's another example. Find the Fourier sine series for f of x is L minus x in this case, and I've also the function is different, and also the interval is different. I want to find the Fourier series sine series representation for this function on the interval 0 to L. Right, so the first thing we do always is to draw it. And let's draw the function in the interval 0 to L, L minus x. So that means that at x equals 0 is L, and then decreases linearly until it hits L, 0 at x equals L. So that's the function we want the other extension. Of course, the whole function would be, if I were to draw it, it would be this line continuing like that. The function, that would be the f of x, right? But we don't want the f of x, we want the h of x, which is the odd extension of this function. Now remember, it has to be odd. So if it has to be odd, because it's the sine series, then it's the odd extension. That means that at the other side of the axis of symmetry, this is I'm drawing the axis of symmetry here, all of them. It's supposed to go through 2L. Another one here goes through L. Another one here, minus 2L. Another one here. Right, so this is one axis of symmetry. So this value has to be the same but negative, right? So it would start at minus L, that would be minus L. And then what it does is the same as that one, it's symmetric with respect to the origin. There we go. So notice that this function is certainly L minus x, but this function is not L minus x. This function here is translated to L to the left. So it's minus x minus L. Okay, this function is minus x minus L. So it's a different function here and here to do the h, but those are the h. The h is piecewise, it's all the h, right? So then here, this extension, we do, again, we're doing the odd extension. So here, the odd extension would continue like this. And here it would continue like that. And then it would go back here to L and continue down and so on. And the same would go here, here at L, minus L, and continue like that, with the same slope. All right, so that would be the odd extension of the function L minus x. Now remember, the function L minus x is this line, and the odd extension is this piecewise function, which is L minus x here, but it's a different function here and a different function here and so on. Okay? All right, so this all line is h of x. Now what is the period of this one? Well, the period is 2L. As you can tell, it repeats every 2L. It repeats this unit or this unit, it doesn't matter. So it's 2L, t is 2L, and that means that omega is again 2 pi over 2L, same as before, then pi over L. Okay. Now this time, we're not going to concern ourselves with computing the a0 and an. We know there's 0 already for parity reasons, because this is the sine Fourier series. So let's compute the bn. Bn is 2 over the period, integral. Let's pick a t0. In this case, t0 is going to be minus L. Or 2 over the period, let's just write the period, 2 over 2L. Okay? And then we have the integral. What are we going to take as the interval? We're going to take minus L to L, right? t0 is minus L. So then minus L to L. Integral of the function h of x. And then sine of n pi divided by L x. All right. Now, if we were to solve this integral as is, we need to divide it into chunks. Do this chunk and add this chunk, which are different functions, right? Remember. But we don't need to. Why? Because this thing is odd, and this thing is odd, and the product of odd and odd is even. That means that I can write this thing 2 over 2 is 1, so 1 over L, and then twice the integral from 0 to L of h of x, which is in this case, if it's from 0 to L, h of x, I know what it is. H of x is L minus x. L minus x sine of m pi divided by L x. Alright, dx. Oh, I forgot the dx here. Dx. Alright, wonderful. So we need to solve that integral. And solving that integral again is one time trivial and then the other term by parts. So I'm not gonna do it. I'll give you one intermediate step. How about it? So intermediate step that I'm going to give you is the following. This thing is 2 over L. Now multiplying minus L divided by n squared pi squared. Alright, and that multiplies L sine of n pi x divided by L. Alright, minus n pi and multiplies x minus L, multiplying the cosine of n pi x divided by L. Alright, and that thing is actually multiplying the whole thing, right? And that thing is evaluated from 0 to L. Substituting the limits of integration, we get 2 over L, and then L n squared pi squared. Notice I changed the sign here, so I'm going to change the relative signs of these two terms. I'm going to reorder them as well. And right, and I get n pi, or L squared, something like that. L squared, there's an L coming from either here or here. L squared that multiplies n pi from this term, and then minus the sine of n pi. All right. Now, easy enough. This thing is 0, the sine of n pi with n an integer. So this thing is 0. So what we get in the end, L cancels the L. I get that the bn's are equal to 2L divided n pi cancels the square, n pi. And these are the bn's. All right, pretty simple bn's. So we can write the sine series for this function that is exactly equal to this function in the interval 0 to L as follows. So sum n equals 1 to infinity, then I write the bn, 2L divided by n pi, and then the sine of n pi divided by L x. Now of course I can simplify a bit, taking factors out. 2 over pi, 2L, sorry, 2L over pi, sum n equals 1 to infinity of 1 over n sine n pi over L x, and that is hx. The sine Fourier series corresponding to f of x in the interval from 0 to L. All right, let's do another, something different that is not a sine series this time. All right, let's do as an exercise 3 the same function, but now I want the Fourier cosine series. Same function, same interval, but I want to do the cosine series. So what I need now, instead of the odd extension, I need the even extension of f of x. All right, so we write L minus x, which is this function here from the interval 0 to L, right? That's straight line. And the function, of course, would continue like that. That's the function. That would be f of x. But we don't want f of x. We want g of x, the even extension. Let's do the even extension. We draw the axis of symmetry. Right? All right. So let's just not confuse ourselves with that. So what is the even extension? Take the axis of symmetry and duplicate the function with respect to the axis so that the same value on both sides of the axis is the same. So this would be the even extension. And then repeat this, even extension here. Even extension, even extension, even extension. It's kind of a triangle pulse, right? Train of pulses. All right, wonderful. So that's the even extension. Now, this time we're going to compute the bn's. We know it's 0. Because of parity, all the bn's are going to be 0. We need to compute a0 and we need to compute an. So let's compute a0 independently, which is the simplest way not to have to deal with limits. It's, what's the period? The period is again 2L. T is equal to L, then same as before, omega equals 2 pi over T, same as before. This thing is pi divided by L. A0, 2 over the period, so 2 over 2L, all right? And then the integral of just the function, this is the function g of x, let's write it. So it's the integral from, let's pick t0 equals minus L, from minus L to L, needs to pick one period, so better from here to here, why not? Of g of x dx, the cosine of 0, which is 1. Wonderful. Then we know this function is even, so let me just write here, simplify, this is 1 over L, but this function is even, so I can write as twice the integral from here to here, right? This area is the same as this area. So I get that 2, this is equal to 2, 0 to L, and then instead of g of x, now I can write L minus x. You see, in here is not L minus x, all right? In here it is L minus x. If I wanted to do this full integral, I would need to write the piecewise version of this and do one integral here and one integral here. I don't have to, because it's even, so it's enough to do that one, and I don't have to deal with piecewise functions. So this in here is L minus x dx. This is 2 over L, all right? And then I get L times x from this integral minus x squared divided by 2 from the integral of the x, right? That thing is evaluated from 0 to L. If I evaluate it, what I get in the end is L, all right? So very simply, A0 is equal to L. We store that value for later. Let's compute AN. All right, so AN, again, 2 over the period, integral from minus L to L, g of x, cosine of, I substitute the period, and is, in this case, pi n pi over L times x dx. Now, this function is even. If I can write even, this function is even. The product then is also even, and that means that I can write that 1 over L that comes from this one, twice the integral from 0 to L of the function L minus x cosine of n pi divided by Lx dx. All right. That's an integral that we do by parts, and let's just do by parts. Let me specify a couple of steps. Again, to do this by parts, let me give you a little bit more details. In the integration by parts, what I did is u is L minus x. That means that du is equal minus dx. Okay. Then dv is equal to the cosine of n pi over Lx dx. And that means that v is L over n pi sine of n pi over Lx. All right, and doing the substitution of by parts integration, I get, I'm doing the full steps here, 2 over L, L minus x, L over n pi, sine n pi over Lx, right, and from 0 to L, plus L n pi, now integral from 0 to L, sine n pi x divided by L dx. I'm doing all the full steps here as because I'm feeling gracious, but very few times I will do the full steps, okay? Then we take another step and we can factor everything together. and we get that this thing is 2 over L, then L minus x, L over n pi, sine of n pi over Lx, minus L squared divided by pi squared n squared, cosine of n pi over Lx, right? And this whole thing evaluated from 0 to L. All right, so we can simplify. We can take, I'm doing full steps. So might as well. Let's just do full steps. Okay, so I'm gonna factor out 2 over L. I'm gonna factor common factor L divided by n squared pi squared. And that multiplies n pi L minus x sine n pi over Lx minus L cosine n pi over Lx, all evaluated from 0 to L. All right, so if I evaluate this, I get 2L divided by n squared pi squared, is simplifying 1 minus the cosine of n pi. All right, wonderful. So we realize that this is correct, right? But we realize that this thing is minus 1 to the n, okay? And that means that this thing is, so let me just write it like that, the an's are equal to 2L n squared pi squared times 1 minus 1 to the n. Aha! So this is one of those cases that the an is 0 for half of the values of n. An is equal to, if n is odd, let us do even first. If n is even, then it's 1 minus 1 and it's 0. 0 for n even. Okay? And then the thing is 4 times, so you see, if n is odd, this is 1 minus 1, so 2 times 2 is 4. L divided n squared pi squared for n odd. All right. So now we have to write we have the result. This is the result. So let's write the series and simplify the series. I'm going to erase everything but the result and the previous step. So we have that an is this value. So one way of solving the exercise that is not full marks, but also not incorrect, we just plug in this in here and substitute A0 by L, and then just, write the sum like that and substitute the omega. But that is not full marks, because that would be a sum that half of the terms are 0. It's not the most simplified form of it. To get full marks and to really write it properly and understanding what you're doing, what I want to write is only the odd terms in here. How do I do that? Well, I realize that this is A0 divided by 2, and I divided this into two sums. The sum of the even ones, n equals 1 to infinity. The even ones would be 2n cosine of 2n omega x, plus the sum of the odd ones, n equals 1 to infinity, a 2n minus 1 cosine of 2n minus 1 omega x. You see, these two sums give this one. This one runs, when n is 1, this runs from a2, a4, a6. This one runs from a1, a3, a5. So these two together combine to that one. Okay, I know that all the even ones are 0. So this one is 0. And then all the odd ones are this, but of course I need to write the a sub 2n minus 1. So this expression, but whenever I see an n, I write a 2n minus 1. So gx, let me just substitute the whole thing. A0 is L. So this is L divided by 2. Okay? And now plus sum, n equals 1 to infinity of all these terms. So I substitute n by 2n minus 1, so I get 4L divided by 2n minus 1 squared pi squared, and then cosine of, and then is 2n minus 1 pi over L times x, which I can simplify a bit. This thing is L over 2, and then put the factors out, plus 4L divided by pi squared, sum n equals 1 to infinity of 1 over 2n minus 1 squared times the cosine of 2n minus 1 pi divided by L x, and that is g of L, the final result, g of x, the final result. Okay? I hope that by now, collecting these terms into odd and even, and just not writing the even ones, writing the odd ones because the even cancel is easy for you now. If not, keep practicing and ask me questions in the review sessions. Alright, so let's do another example. Before moving to another example, let's just do another exercise of simplification of this kind of equalities now when the odd ones are the ones that cancel. Imagine that you're computing the cosine Fourier series of a function f of x such that the result that you get for the AMs is this one. So of course you can just copy the AMs and write it like that in the series, but then let's simplify, because here you're summing too many terms. Some of them are 0. So we know that this AM that we have here, let's write here, AM is, when n is even, then that thing becomes 8 divided by pi squared n squared for n even, and then it becomes 0 for n odd. So it's the opposite as before. Okay? Okay, so if we want to simplify that, then we know that the f of x, of course, can be written. Let me just write, normally you can do this in one step, but I'm going to do the 2 steps. I can separate the sum into the even and the odd contributions. First the even ones, 2n cosine of 2n omega x plus sum n equals 1 a 2n minus 1 cosine of 2n minus 1 omega x. Alright, these two together give me, so let me just write it like that, these two together give me the sum n equals 1 to infinity an cosine of n omega x. Alright, this sum contains all of the terms for all subindices an, 1, 2, 3, 4, 5. This one contains 2, 4, 6, 8. This one contains 1, 3, 5, 7, etc. Now in this case we know that these ones are 0. We are left with the even ones, so that would be f of x equals a0 divided by 2 plus sum n equals 1 to infinity a to n cosine of 2n omega x. Alright, but then I need to write the 2n, a sub 2n. That means that if this is a of n, a sub n, a sub 2n, well, I write 2n when I raise the n and n, right? So it's a divided by pi squared over 2n squared. That is a 4, and the 4 simplifies the 8. So I get 2 over pi squared n squared. That's a sub 2n. Okay? Alright, so then I substitute here, and I get a0 divided by 2, plus I take all the factors out, so that would be 2 over pi squared, and then this would be sum n equals 1 to infinity of 1 over n squared, and then cosine of 2n omega x, whatever omega is in this case, alright? So this is a case in which the odd ones are the ones that cancel and the even ones stay. Here's an example of how to simplify these things. Alright, let's see another example. Now a proper one. Let's do a full range expansion, and this one's going to be long, so be prepared for it. Alright, so find the full range Fourier series of that function over there, L when x is negative, and 2x when x is positive. On the interval, I want the full range expansion on the interval minus L, x, L. So I need to find the periodic extension, f of x, capital F of x, the periodic extension of small f of x. Alright, let's first draw the function here. What is the function? I'm going to draw it in blue. the full function is L for the negatives, so the function is actually for the negatives is L, so a constant like that, that would be the function. And for the positives is actually 2x, so it starts like that and goes to 2L, like that. That's the function for the positives, and it would go all the way up. This is not curving, right? It's just a straight line all the way up. That's the function. And it's there in the whole real line, but we don't want that. We want the Fourier, full range Fourier series in this interval. So that means I need to get that interval and do the periodic extension. Let's draw the periodic extension in black. The periodic extension, it's easy. I just take the function and again repeat it in the axis of symmetry. So this one would be up to 2L like that, and then here it would go up to 2L. Let's see. This is, remind that this is 2L. So like that. All right, and this go here. And the same goes here. I take this, so this one would be to 2L, which should be here. Let's see it like that. And then from here on, it would be this. And then here it would be like that, and so on and so forth, right? So now forget the blue, is the black one. So it's, now I'm gonna draw this one on top, of course, because here is the same. Of course, they coincide in the interval where you compute the Fourier expansion. So you just take this unit and repeat it to the left and to the right infinite times. That's the periodic extension. Now, what is the period? Well, you can tell that here the period is 2L as well. It repeats every 2L. And that means that omega is 2 pi over t, so it's equal to pi over L again. All right. Now this one will have a 0, will have a n, and the n in principle. So if I have to write the full expansion, I need to write it. I need to write the full Fourier series. Let's just write it like that. Capital F of x will be equal to a0 divided by 2 plus sum n equals 1 to infinity, an cosine of n omega x plus sum n equals 1 to infinity, bn sine of n omega x. Wonderful. All right, so let's compute all of them, and let's begin with a0 as usual. So a0 would be the integral from 2 over the period, right? So 2 over the period is 12, 2 over 12. Integral from, what do we take at t0? Well, minus L, of course. Minus L to L. To L, the L, from minus L to L, there's a 2L period, of course. And then this thing would be the integral dx of capital F of x. Now, I'm getting you more used to having the differential first. That's the best way for me not to forget. That's the way I usually write it. And you should get used to that by now. Now, what is the problem with this? The problem with this is that in this case, the function has no parity in between the interval. And then from here to here is one function, and from here to here is another function. So I need to divide that integral in two. This integral is going to be 1 over L, common factor of the integral from minus L to 0 dx times L plus the integral from 0 to L dx to x. Right, so not too difficult for that case, but we're going to have to split the integrals into intervals, always in this case. For a0 is simple, so this thing gives me 1 over L, that multiplies. The first one gives me Lx, I'll write it, Lx from minus L to 0, okay? Plus this one is x squared divided by 2, that cancels the 2, all right? So this one is x squared from 0 to L. If I substitute the limits, I get that a0, I'll write it up there because it's the final result. Well, I'll write it here. a0, it's equal to 1 over L, and then I get L squared from this one, L squared plus L squared, and that gives me 2L. So a0 is equal to 2L. All right, so now we need to find an. So let me actually erase the calculation of a0 to write an in the full extension of the board, because there's two integrals that we have to solve. The coefficients an are, of course, 1 over the period, so in this, 2 over the period, which in this case is 2 over 2L. Now integral from minus L to L dx. I'm going to be writing the dx first. Get used to it, please. If you are not used to it yet, patience, my friends. It's a more convenient way of writing it. Trust me, it's a favor I'm doing you for the future. Please get used to it. That way I won't forget the dx. So this is f of x, and then we have the cosine of substituting omega n pi over lx. Alrighty. Now, the problem with that is that f of x is a piecewise function. So it's one form from minus L to 0 and one form from 0 to L. So that means I get 1 over L, common factor, of two integrals. The integral from minus L to 0 dx L cosine of n pi over Lx. And then plus the integral from 0 to L of dx of 2x cosine n pi over Lx. And we need to do these two integrals. So let's deal first with I1. I give them names, all right? So this one is I1, and I call this one I2, okay? I1, it's very easy. I take the L out, so this is L, integral from minus L to 0, dx, cosine, n pi over Lx, all right? But that's simple. It takes an L out and n pi out when I integrate, so it's L squared divided by n pi, and now I get the sine of n pi L over x evaluated from minus L to 0. But that's nice, because the sine of 0 is 0, and the sine of minus n pi is also 0. This integral is exactly 0. Wonderful. So I1 is 0. This is just me being happy about it being 0, because it means I don't have to write it later. So maybe I should write more like this. Although that's the symbol we use for proof, but whatever. Maybe I can do it like that. All right. So let's do I2. I2 is, I take the 2 out, is twice the integral from 0 to L dx x cosine n pi L over x. This is a very simple by parts integral. So let me write the by parts, the parts that I do on this side of the board. All right, so u, in this case, I can call it 2x. I can put the u, yeah, let's do it like that. All right, I can call the u 2x. It doesn't matter really. So du is just 2 dx. And then dv, it's equal to the cosine of n pi over Lx dx, which means upon integration that v is equal to L over n pi sine n pi over Lx. Okay, I substitute the by parts here, and I get first 2Lx over n pi sine n pi over Lx evaluated from 0 to L. All right, and then minus 2L n pi integral 0 to L dx sine n pi x over L. All right, but that integral is really easy, because this integral, let me write it here, is just L, actually minus L, right, minus L divided by n pi, the cosine of n pi xl, then the minus with the minus will cancel, that gives me an L squared, and then an n pi squared, that's where it's going to come from. All right, so this thing is equal to, let me write it here, common factor 2L over n squared pi squared, all right, and then I took the same common factor here, but this didn't have an n pi square in the denominator, only n pi, so I multiply by an extra n pi. All right, so n pi x sine of n pi x divided by L plus L cosine n pi x divided by L, all of it evaluated from 0 to L. Okay, nicely enough, when I evaluate from 0 to L, I get here the sine of n pi and the sine of 0. So this whole term goes to 0 when I evaluate the limits. All right, so, and then let's evaluate the limits on the other one. So I get 2L divided by n squared pi squared. And then I get that multiplies L cosine of n pi minus L cosine of 0, which is 1. Aha, but that thing is 2L squared divided by n squared pi squared minus 1 to the n minus 1. Remember, this is minus 1 to the n. All right. Now, that's I2, that's the result of I2. I can plug it into the expression of AN. The only difference is because I1 is 0, it's just a factor 1 over L. So AN is equal to 2L divided by n squared pi squared multiplying minus 1 to the n minus 1. Now, of course, that means that this is one of those cases where half of them are 0. We see that AN is equal to 0 when n is even, is 1 minus 1. And then when n is odd, this is a minus 2, so it's minus 4L divided by n squared pi squared. All right, so we have AN. We need to compute BN. Let's move AN up there and let's erase the board to compute BN. Okay, now that we have the AN there, we can write BN. It's 2 over the period, 2 over 2L, integral from minus L to L, dx, f of x, then sine of n pi x divided by L. Same as before, we need to divide it into two integrals. So we have a common factor 1 over L, and then we write this as an I1, I3 plus I4. Okay? All right, so let's solve them. What is I3? Well, I3 is from minus L to L. So I3 is the integral of 1 over L, is the integral of minus L to 0 dx, f of x from minus L to 0 is just L. So L sine n pi x divided by L. All right? Okay, we can solve this one directly. And what we get is minus L squared divided by n pi cosine of n pi x divided by L. And that is evaluated from minus L to 0, which gives me L squared n pi minus 1 plus the cosine of n pi. So this thing, the cosine of n pi is minus 1 to the n. So this thing is L squared n pi minus 1 to the n minus 1. Okay, so this is I3. We need to do I4. So I4 is very similar to the other one, to I2 when we did it. I4 is the integral of from 0 to L, right? Is the other half. Again, I3 and I4 is divided minus L to L, from minus L to 0, and from 0 to L. I4 is from 0 to L, so it's 2x, it's dx, 2x, sine n pi x over L. All right, so this thing we do by parts, very similar to before. In fact, I make the same choice. dv would be now the sine instead of the cosine. And then v would have a minus sign here and would be the cosine here. All right, so we do very similar calculations to what we did before. I'll write the simplified expression, 2 over L after taking common factors, n squared pi squared, that multiplies minus n pi x cosine of n pi x divided by L plus L sine of n pi x divided by L, and that is from 0 to L, evaluated. Now if we do that evaluation, we get that I4 it's equal to common factor here 2L divided by n squared pi squared. All right, and now that multiplies minus n pi L cosine of n pi plus L sine of n pi, where I already substituted that the sine of 0 is 0 and the cosine of 0 is 1. Now, of course, this term here is also 0, the sine of n pi is 0, so that I'm left with is this guy, but also the cosine of n pi is minus 1 to the n, okay? So this thing is simply minus 2L squared from this L divided by n pi minus 1 to the n, or what is the same, 2L divided squared divided by n pi multiplied minus 1 to the n plus 1. Alright, we can write now Bn, which remember is equal to 1 over L I3 plus I4. Substituting I3 and I4, we get the following. 1 over L multiplying L squared divided by n pi, and that multiplies minus 1 to the n, minus 1, minus 2L squared divided by n pi, minus 1 to the n. Oh, nice. I can sum together the coefficients of minus 1 to the n, and what I'm left with is minus L divided by n pi, 1 plus minus 1 to the n. I didn't do any magic here. All that I did is I have L squared n pi minus 2L squared n pi multiplying minus 1 to the n, common factor. Okay, so I'm left with just minus L squared n pi. And then I change the sign of the minus 1, putting the sign outside, and I get this. All right, look at this. We get the other case here, which is really nice. So we get that Bn, it's equal to, when n is even, this is 1 plus 1, so this is a 2. So when n is even, I get minus 2L divided by n pi, n even, and I get 0 for n odd. All right, now, well, let's collect them together and finally write the full Fourier series, the full range expansion. All right, so that we have to do, now that we have all the coefficients collected, is write the f of x. Now, keep in mind, I'm going to write it here, taking into account only the terms that survive. So I have a0 divided by 2, that's the same. For the cosine expansion, only the odd ones will survive, so I'm not going to write the even ones, I'm going to write only the odd ones. And if you remember the previous exercise, that's the sum n equals to 1 to infinity, a to the 2n minus 1, cosine of 2n minus 1, omega x. That's only the odd summands in this sum. And for the sine, it's only the even ones. So n equals 1 to infinity, b 2n sine 2n omega x. All right? Now, from here, let me just write quickly the a 2n minus 1. a 2n minus 1 would be minus 4l 2n minus 1 squared pi squared. And of course, the b2n, it's equal to minus 2l 2n pi. So it's just a matter of substituting now. F of x, it's equal, a is 2l, so 12 divided by 2 is just an l. Now, I'm gonna take all the common factors out. So, I get, let's see, how many common factors? Well, I'm gonna take them separately. Let's do first the cosine one. So the cosine one has a minus 4l divided by pi squared, and then sum n equals 1 to infinity. And then I'm going to separate this because this is going to be conflicting a bit. And then I get the rest of the coefficient, 1 over 2n minus 1 squared. And now I have the cosine of 2n minus 1, and I substitute the omega pi divided by L times x, that will be the cosine term, and then minus, let me write minus here. Now the sine terms. For the sine terms, I take out a 2L divided by 2. Ah, nice, the 2 cancels. I didn't cancel there. So it's just an L divided by pi. Okay? And that multiplies the sum, n equals 1 to infinity, whatever is left of the dn. So it's just 1 over n. 1 over n sine of 2 pi divided by L x n, sorry, 2 n pi divided by L x. There we go. And that, my friends, is the final result. That is the full range expansion of f of x in the interval minus L to L. I hope that this is clear. It's plenty of practice. You will have assignments to practice too, and of course we have the review session for you to ask me questions. But that's it for now, and then in the next video we will see new material about the Fourier series.